In this video we are going to see about derivation of the divergent equation, scale analysis of divergent equation, and physical significance of each terms. Here, the derivation is derived from horizontal vector form of momentum equation. The given horizontal vector form of momentum equation written as in zonal and meridional form. This equation represent zonal momentum equation, whereas this equation represent meridional momentum equation. This represent as local rate of change of zonal and meridional velocity component. Yellow color noted variable represent as advection. The left side blue terms represent as pressure gradient force. The green term represent as the Coriolis force. The last term shows friction force, sometimes we refer as viscous force, while dealing with fluid. Now, differentiate equation 1, with respect to x. And equation 2, differentiate with respect to y. After differentiation equation 1 with respect to x, and differentiate equation 2 with respect to y, we get this result. So add the equation 1 and 2. We get this added result combined. We know that variation of Coriolis force and zonal is negligible. Now arranging each term from square brackets to get our result. Replace the relative vorticity and beta parameter with a notation. Here also replace this variable with divergent term. Advection of divergent term will become 0. Here our final result for divergent equation. After scale analysis of the divergent equation. Neglecting smaller terms, if we consider divergent free, then these two terms will neglect. The final equation will be frictionless, horizontal flow, and divergent free. So this equation is named as balanced form of divergent equation. The final equation is independent on time, so it referred as diagnostic equation.